Hi everyone. In this video we're going to be taking a look at a bit more complex of a kinematic problem than the previous video. The previous one was just a one-step, one equation problem. This video we're going to be taking a look at a bit more difficult, or at least more things to do in the problem. So the problem setup is that there's a construction worker on top of a 130 meter tall building. So this is 0 meters and the top is 130 meters. And he is going to accidentally drop his hammer from the top of the building. And there are three things that we need to solve for. Part A is going to ask us to solve for the speed that the hammer hits the ground with. So what speed, VF, does the hammer hit the ground? Part B is how much time passes between when the hammer is dropped and when it hits the ground, delta T. And problem C is, or not problem C, part C of this problem, what fraction of the total airborne time does the hammer spend in the top 75% of the falling distance? So 75% delta x time. Three parts to this problem. So what do we know? We know that delta x is, so if this up here is xi and this down here is 0 meters is xf, this minus this would be negative 130 meters. Sure, let's go with that. Let's say that down is positive. So 0 minus 130 delta x is negative 130 meters. So down is positive. And then we also know that there's constant acceleration, and that's just the acceleration due to gravity. So A equals G equals negative 9.8 meters per second squared. What else do we know? This isn't explicitly stated, but if you're clever enough, you'll figure out that he drops the hammer from rest, okay? So VI, the initial velocity, is 0 meters per second. What do we want? We want to find, in part A, the final velocity. So let's work out part A first. The final velocity, it looks as if, so again, I think we can use the time independent kinematic equation, as there's no time mentioned here, but there is everything else we need. So we're just going to plug all this into this third equation here. There will only be one unknown. We'll algebraically solve for that. So let's use equation 3, which says that the final velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement. The final velocity squared is what we're looking for. The initial velocity squared, the initial velocity is 0. 0 squared is 0. 0 plus 2 times A, negative 9.8 meters per second squared, times delta x, negative 130 meters. This is going to come out to, so the final velocity squared is equal to, let's see, the negatives will cancel out. 2 times 9.8 is 19.6. So this is going to be 19.6 meters per second squared times 130 meters. So the final velocity, VF, is equal to the square root, right? Take the square root of both sides. 19.6 times 130 meters squared per second squared. So the final velocity is equal to the square root of 19.6 times 130 meters squared per second squared square root. And if you put that in your calculator, you will see that this comes out to be 50.47 meters per second. The hammer hits the ground, the instant before it hits the ground, it's traveling at 50.47 meters per second. It's quite fast. That's part A. Part A done. Part B is going to ask us to find the total amount of time it takes from when he drops the hammer to when it hits the ground. Okay, so we're looking for an amount of time, which tells us that we cannot use the time independent kinematic equation because there's no time present there. We can use the first. I think the first is going to be the easiest. So there's part B. The final velocity is equal to the initial velocity plus the acceleration times time is equal final velocity we just calculated. Okay, so we needed the result from part A in order to solve part B. 50.47 meters per second is equal to 0 meters per second plus, actually minus 9.8 meters per second squared times our delta t that we want. T is equal to delta t if the initial time is 0. I'm just calling it delta t because it's a elapsed amount of time, not an instant in time. This goes away. Okay, so I actually made a mistake. So if down is positive, so let's say here's the building, here's the ground, he drops the hammer from here. If down is positive, then this is positive, and so is this. If down is negative, this would have a negative sign. But I think in part A, I selected down as positive. So there shouldn't have been a negative sign for gravity before, but it worked out because there were two, so they canceled. Anyway, this has a plus sign, this has a plus sign. Let's divide both sides by 9.8 meters per second squared. So the total elapsed amount of time is equal to 50.47 meters per second squared divided by meters per second, it's a velocity, 9.8 meters per second squared. If you calculate this, you will find that it's equal to 5.15 seconds. The total amount of time it takes from when the guy drops the hammer at the top of the 130 meter building until it hits the ground with this speed is 5.15 seconds. That's the total amount of time that it takes. And that's our answer to part B. There's one part left. One part left, which is part C, and it asks us to find the total amount of time delta t as a fraction of our answer to part B, which was 5.15 seconds, that the falling hammer spends in the top 75% of the falling distance. So the total falling distance, we know delta x is equal to 130 meters. The top 75% of that obviously is equal to 0.75 times 130 meters, which is, let's see, 97.5 meters. But we are interested in the top 97.5 meters. Of course, the hammer is going to be traveling slower in the top 75 meters, the top 97.5 meters than the bottom 97.5 meters, because it'll accelerate as it falls downward. the top 97.5 meters. Let us use, let's use the second equation. Let's use the second equation. The final, xf is equal to xi plus vit plus 1/2 at squared. What are we interested in solving? We're interested in solving for t. We want t, the total amount of time that it spends in these top 97.5 meters. On first glance, it doesn't look good to use the second one because it looks like we'll need to solve the quadratic equation to get t, but since it's the top 97.5 meters, the initial velocity is 0 because he drops it from rest, and the xf minus xi, if we subtract the initial position from both sides, we're going to get 97.5 meters, okay, because that's the displacement over which we are concerned about the time. So 97.5 meters is equal to, this term is 0, half the acceleration times the time squared, which is equal to 1/2 times 9.8 meters per second squared times time squared. Multiply both sides by 2 and divide both sides by 9.8. So we're going to get 2 times 97.5 meters divided by 9.8 meters per second squared is equal to t squared. To obtain t, take the square root of both sides. T is equal to 2 times 97.5 meters over 9.8 meters per second squared square root, and if you solve that, it comes out to 4.46 seconds. So in order to drop the top 97.5 meters, it takes 4.46 seconds, which, as you can see, is a significant fraction of the total amount of time, 5.15 seconds. Let's obtain the fraction right now. 4.46 seconds over 5.15 seconds is 86.6%. 86.6% of the total amount of time is spent in the top 3/4 of the distance it falls. That's the power of acceleration. So this was a bit more of a complex problem than the one in the previous video. There were 3 different things we needed to solve for, 3 different parts of the problem. And in each part we ended up using actually a different equation. So it was good practice using the 3 different equations. What's interesting to mention is that we actually could have solved part B a different way. So there are multiple ways to obtain the correct answer for any given, really for any given physics problem. There are always multiple ways to obtain the correct answer. Same thing in math, really. We could have solved, so alternate solution to part B. We could have used equation 4, delta x equals vf plus vi t over 2. In part B, we were solving for t, so that's 2 delta x over vf plus vi equals t equals 2 times 130 meters over, what was that, 50.47 meters per second plus 0, and this is also equal to 5.15 seconds. So there are multiple ways to obtain the correct answer. Could have used 2 different equations. In my notes, I chose to solve it using this one, but while making this video, I arbitrarily chose to solve it using this one. Same amount of algebra steps, but it's important to note that there are multiple ways to do it. So in the next video, we will take it one level of complexity higher and take a look at kinematics problem with not multiple parts to the problem like this, but multiple steps of the problem. So thank you for watching.